Buon pomeriggio, benvenuti a questo nuovo seminario LAG. È un piacere per me oggi avere come conferenziere il professor Alessandro Berarducci dell'Università di Pisa. Alessandro Berarducci è un grande esperto di logica matematica e fondamenti della matematica e oggi ci parlerà nel suo talk dal titolo From Transeries to Surreals and Applications. Lo ringrazio di aver accettato l'invito a tenere questa comunicazione nell'ambito di questi seminari. Per me è veramente un piacere averlo come speaker. Prego.
Okay, thank you very much, Giovanni. I'm very pleased and honored to speak in this conference. And so I will speak about transeries and the connections with the surreals, some recent connections, and possibly some applications at the end. Okay, let me begin with the notion of Hahn field, the Hahn field of generalized series. This is the most technical slide, so don't be afraid. Afterwards, it will be easier. So we start with a group, which I write in multiplicative notation, a group M of monomials, but it's abelian, even if it's in multiplicative notation, ordered. And then I may consider the field of all formal series with monomials from M and real coefficients. So it's a field consisting of formal sums where indexed by an ordinal, alpha. So these are not ordinary series that may be transfinitely long. There could be an infinitely many sums followed by another block of infinitely many sums. The monomials form a decreasing sequence because the idea is that the terms in the sum must become smaller and smaller. And the coefficients are reals. So you consider all these formal sums, generalized series, and you obtain a field. So sum and product and order are defined in the natural way. So for the order, you consider the leading coefficient. If it's positive, the whole series is positive, otherwise it's negative. And it's important that the index is an ordinal and not the index set and not an arbitrary ordered set, because otherwise you will have difficulties in defining the product. Because when you define the product of two such objects, the risk is that you are going to sum infinitely many times the same real number. So in this way, it works. So this is a construction, a general construction due to Hahn in 1907. And it's a universal way of obtaining ordered fields. So every ordered field embeds in one of these Hahn fields. You can also consider infinite sums of infinite sums. So you have a family of Fi, of objects of formal series, and you may want to sum them. So you have a notion of summability, very important. So a family is summable if there are no weakly increasing sequences of monomials such that each of these monomials belongs to the support of some Fi. So the support, it means appears with a non-zero coefficient. So in this case, you can define the sum in the natural way, no? Monomial by monomial, and then you obtain something reasonable. So it's a formal notion of summability. There is no convergence or anything like that, but there is a notion of summability in this context. Okay, so if there are questions, please interrupt, because this is really the most technical part and you need to understand this well. Feel free to interrupt anytime. Okay. Now, I will consider objects of this kind, fields of generalized series. Okay, let's begin with an easy example that everybody knows, Laurent series. Laurent series, you take as a group of monomials, you take a variable omega, and you think of omega as tending to plus infinity, not to zero. So it's bigger than any real, say. You can order this field by saying that omega is bigger than any constant. You consider as a group of monomials all the integer powers of omega. And then you take you know, the Han field, the Han series in this case are just the Laurent series. For instance, the one I just wrote there, 3 omega squared plus 5 omega plus 7 plus 2, 1 over omega, blah, blah. So you get, in this case, finitely many infinite terms, 3 omega squared plus 5 omega. Then you have a constant term, 7, and then you have a very long infinitesimal tail, no, with terms with the negative powers of omega, which are infinitesimal because omega is infinite. Omega, I take it to be tending to plus infinity. So this is the first example of that everybody knows. If you go to the Puiseux series, then it's not an Han field, but it's a subfield of an Han field, because in this case, you may take as a group of monomials the rational powers of omega, because you also want roots, say omega, square root of omega, omega to the 1/2. But you don't take all the possible sums indexed by an ordinal, no, well ordered, but you only take those in which the support is finitely generated. So, which is exactly the union that I wrote there. So this is the field of Puiseux series. Of course, one may also consider the bigger field in which you take all possible sums, not only the ones that are finitely generated. Okay, now my goal is to construct fields of this kind in which you also have an exponential and a logarithmic function. And these are going to be the trans-series. So some exponentials can already be defined in the Laurent series, because you can define in the Laurent series the exponential of an infinitesimal element. For instance, the exponential of 1 over omega, you simply use the Taylor series of exp, and you get a nice Laurent series, sum of omega minus n over n factorial. However, you cannot do the same, you cannot use the same formula to define exp of omega. You can do exp of 1 over omega, but not exp of omega, because then it's not summable, because you would get omega to the n, which becomes bigger and bigger rather than smaller and smaller. So it cannot be, it's not formally summable. So indeed, in the Laurent series, you cannot define a global exponential. However, you can define the exponential of every infinitesimal element, not only 1 over omega, but any other infinitesimal element can be plugged in, and you expand it and get a Laurent series. Similarly, for the log, you don't have a global log, but you have a partial logarithm. You can define the logarithm of the elements which are infinitesimally close to 1, no? 1 plus an infinitesimal. For instance, log of 1 plus 1 over omega, you just apply the Taylor formula, and you get something which makes sense as a Laurent series. However, to define a global exp and a global logarithm, you need to go to a larger field, and this is going to be the field of trans-series, which necessarily contains more monomials, because here we don't have enough monomials to define exp and log. Okay, so adding more monomials. So, okay, let's first observe, I already did it, but in any field whatsoever of containing the Laurent series, it doesn't make sense to define exp of omega as sum of omega to the n over n factorial, because omega to the n increases with n. Remember that omega is infinitely large, and instead it should decrease. So this doesn't make sense. So it's not summable in the technical sense explained at the beginning. Okay, so the remedy, how do you do it? The remedy is to adjoin a new monomial. You simply take exp of omega, e to the omega, as a new monomial. You enlarge the group of monomials, and also log of omega, together also with the products of monomials also should be a monomial. And maybe you also want the compositional iterates exp n times of omega, and the same for log. Okay, now you have new monomials, so you can have new series. I will postpone or maybe omit the formal definition because it's kind of complicated, but let's do some examples so you see what's going on. So f to the g is, of course, defined as exp of g log f. Okay, let's do some experiments. Suppose you want an asymptotic expansion of omega plus 1 to the omega for the variable omega tending to plus infinity. So you want to do some kind of asymptotic expansion. Well, then, of course, you can write it in the form omega to the omega multiplied by 1 plus 1 over omega to the omega. And this is omega to the omega e to the omega log of 1 plus 1 over omega. This log can be computed using the Taylor formula, because log of 1 plus an infinitesimal can be computed using the Taylor formula. So you plug it in and you get the third line. And now you have e to the omega and then an infinite sum, but this infinite sum is an infinitesimal. Well, omega cancels out. This infinite sum begins with omega to the minus 1. So you multiply it by omega outside, you get 1, and you take it out, so it's e to the 1. And then you remain with e to something infinitesimal. Since it is infinitesimal, you can apply the Taylor formula for exp, and you get a family of epsilon n over n factorial, where epsilon is itself a series, so it's a sum of sums. But you can reorder it because epsilon is infinitesimal. You can reorder it in a good way, and it's summable, and so you get something which makes sense. It's a formal series containing a new monomial, which is omega to the omega, and then some old monomials, which are just the powers of the integer powers of omega. Okay, this is an easy example, but things soon get more complicated. Now, suppose you want to do a small perturbation of this example. You do omega plus 1 plus a small perturbation to the omega. Small perturbation could be, for instance, omega to the minus omega. Well, say 1 over omega to the omega. And then you discover that you need this series of transfinite ordinal length. So you take this small perturbating term, 1 over omega to the omega or omega to the minus omega. You do the same as before, omega plus 1 plus epsilon to the omega. You do the obvious computations. You keep expanding with the usual rules of log and exp. So here you expand the log using the Taylor formula because it's a 1 plus an infinitesimal. And then I simply expand this infinite sum explicitly, so you see what's going on. Okay, then I also need to expand e to the 1 plus epsilon. So I separate, this is e to the 1 times, so which is e, times e to the epsilon. E to the epsilon, I apply the Taylor formula for exp, and so I get this sort of object. But then this is not ordered in the correct way. I should reorder the monomials in a decreasing order. And then I discovered that I get infinite blocks of infinite sums followed by other blocks of infinite sums. So it's something which has order type very bigger than the usual order type. And so it's not finished, the computation, because now I should also expand e to that negative power. I should expand the last expression, which can be done by the terror series. Once you do it, you get a trans series, which with blocks of infinite sums followed by other such blocks. So it has a transfinite ordinal length. So this is the kind of objects that we are going to consider. Okay, what is the formal definition? So what are the monomials which are allowed? And it's not completely easy, but let's first mention the use of these objects. So, well, the most important result has been probably the one by Carlo, that used the trans series in order to give a solution to Dulac's conjecture, namely part of Hilbert's 16th problem, so the finiteness of limit cycles in polynomial planar vector fields. And the proof uses in an essential way this trans series, this development of trans series. So these are kind of asymptotic developments, very formal, but then Ekal has a method to do some ability, to associate to this formal object some real functions. So they are also used in model theory, but there are very important work by Aschenbrenner, Van den Dries, and Van der Hoeven, and also computer algebra by Van der Hoeven, formal automatic integration and similar things. Okay, one of the reasons they are so useful is that they can, well, first of all, they can be formally differentiated. You can define the derivative in the obvious way. The derivative of the variable omega is 1, because omega represents the identity function some way. The derivative of the constants, the real constants, is 0. The derivative respects exp and log. So the derivative of exp of f is exp of f derivative of f. Same for log, similarly for log. You have Leibniz rule for the derivative. And then you require also that the derivative distributes over infinite sums. Okay, this is not surprising that they can be differentiated. What is more surprising is that they can be integrated. Every trans series has a formal integral, namely antiderivative. So formal integrals can always be defined, of course, up to a real constant. For instance, the integral of 1 over omega is log omega, right? So which is something which you don't have in the Laurent series, but you have in the trans series. This log omega is a new monomial, which serves as an integral of 1 over omega. But you have also more complicated integrals, like the integral of e to the minus omega over omega. So it's one of the, you get some nice trans series out of it, which you may notice doesn't make sense. I mean, it's divergent. It doesn't make sense as a real function because it's divergent, but it's formally correct. So if you take the right-hand side and you take the derivative, you get e to the omega divided by omega. This is an example due to Euler, I believe. But anyway, you have these formal computations. You have a very big field closed under exp, log, integrals, derivatives, and integrals. So it can be used for the formal solutions of a lot of nice differential equations of certain types. Everything is very formal, but then you will see that can also be applied to real analytic applications. Okay, let me give some formal details here. So to recap, every trans series is a formal sum of the terms are real times monomials. Then you have real coefficients. The length is an ordinal. The monomials are decreasing. So it's a decreasing sequence of transmonomials, so monomials occurring in the transseries. Now, transseries exist in various variants. Now I'm considering here the grid-based variant, which is the one considered by Carlo. Namely, it requires that the subgroup, the support of any series is finitely generated. So the subgroup generated by the monomials appearing in a series is finitely generated. This is a technical point. Now, what are the transmonomials? The reason why it's complicated, the definition of the transseries, is that the definition of the transmonomials is done by a simultaneous induction than the definition of the transseries themselves. So you start with a few transmonomials, for instance, the iterated logs of omega, and then you keep going, starting from this. So what happens is the following. Once you have these initial transmonomials, you can start forming sums using such transmonomials. But then once you have a sum, you may use, you can try to apply exp of that sum. And exp of that sum, there are two cases. Either you have to introduce it as a new monomial, because otherwise you don't know what to do. And this is the first case when all the MIs are bigger than 1. You are forced to introduce a new monomial to define exp of that formal object. Because if a monomial is bigger than 1, it's automatically infinite. So exp of infinite is more complicated. If instead all the monomials are less than 1, and therefore they are infinitesimals, and then you can compute exp of that formal sum using the Taylor series of exp, and you get something which is summable, so it can be expanded and reordered in the correct way. So in this case, in the second case, the expression that can be expanded and evaluated without introducing new monomials. So it's the two sides of the board interact. So you have some initial monomials and some partial and some sums. Then once you have some sums, you get some new monomials, which are needed to define some new exponentials. And so you keep going back and forth. And then you get at the end the field of transseries. Okay. Now, just a technical remark. So the field of transseries is not a Hahn field, is not the field of all possible sums that you can do with the given monomials. There are certain sums, for instance, the sum of log n times of omega, log of omega. In principle, this looks as a perfectly good object because log n of omega is a transseries, it's a monomial. Log n of omega is summable because it's decreasing, so it's a decreasing sequence of monomials. Log omega, log omega, log omega, it's decreasing, so it looks correct. Nevertheless, for some technical reasons, you don't want this to be a transseries. So there are certain sums which you don't like to have, you don't want, despite the fact that they are in the Hahn field of all possible sums. So the transseries are a subfield, are a proper subfield, like the Puiseux series that we have seen before. So in particular, the sum that I wrote, sum of log n, the support is not finitely generated. Okay, why these technical restrictions? These technical restrictions are the price to be paid in order to have the possibility of defining a global exp and also integrals. If you don't put some restrictions, there is no chance, this has been proved by Shelah and Kuhlmann, you cannot have a global exp unless you have you do some, in a Hahn field, which is a set, you don't have a global exp. Anyway, so just some formal details. Now, with Vincenzo Mantova, an ex-student of mine, who is now in Leeds, we discovered that the transeries are connected with Conway serial numbers, which is kind of surprising. Conway serial numbers, the motivation for Conway's serial numbers came from combinatorial games like chess or Go, so have nothing to do with all this. But transeries can somehow be embedded, isomorphically embedded in Conway's field of serial numbers. And moreover, we can define a derivation on the serial numbers, extending the derivation on the transeries. And the advantage is that, unlike the transeries, now we have no artificial limitations on the possible sums that we can take. We will see that the transeries can be represented as formal sums. And this time you have the sum of all possible families. So this is the situation. You have Laurent series, Puiseux series, transeries, serial numbers. Suppose they are cars, right? And so you have, desired properties, the color, the radio, whatever, and in this case, you have the desirable properties it's a field, it has derivations, integrals, exp log, roots of positive elements, arbitrary sums of all possible summable families. And you will see that the serials are the best of all because well, of course, the Laurent series do not have an exp log, but the Laurent series don't even have roots. Square root of omega is not allowed. The Puiseux series have roots, but they don't have all possible sums because omega to the 1 over n, despite the fact that each of them, each omega to the 1 over n, each term is a Puiseux series, the whole sum is not a Puiseux series. Because it's in the transeries, you have a similar problem. Each log n of omega is a legitimate transeries, each of them, but the sum of all of them, despite it's summable because it's decreasing in the correct way, it's not a possible transeries. Of course, transeries have the advantage with respect to the Laurent series to have an exp log and also in integrals and derivatives, but they lack something which is arbitrary infinite sums. In the serials, you have everything. So let's introduce the serials. What are all these serials? And the new thing is the derivation and the integrals that have been recently discovered. So what are the serials? Well, first you need to recall what are the ordinals. 0 is an ordinal. If alpha is an ordinal, alpha plus 1 is an ordinal. The sup of a set of ordinals is an ordinal of a set. But the ordinals are not a set. It's a proper class, as Giovanni knows very well, having read my notes. So that means that the class of all ordinals cannot be a set. Otherwise, you could take the sup and you would get a new ordinal. So the first few ordinals have a name, 0, 1, 2, omega, omega plus 1, omega plus 2, omega plus omega, which you call omega times 2. Then you have omega times 2 plus 1, omega times 2 plus 2, omega times 2 plus omega, which is omega times 3. Then you get omega times omega, and so and so. The serials are a kind of binary version of the ordinals. So instead of having a successor, you have two successors, which is you call left child and right child. So let me skip this. So these are the serials. So you start with 0, then you have two childs, which you call -1 and 1, left child and right child. Then -1 has two childs, which you call -2 and -1/2. And 1 has two children, which you called 1/2 and 2, and so on. So, okay, how do you want to define a sum and a product of serial numbers? So a serial is, mathematically speaking, a transfinite binary sequence. It's a function from an ordinal to a binary set, which tells you if you go left or right. So the nodes of the tree are surreals. On the left and branch, on the rightmost branch, you have the ordinals. You see 0, 1, 2, 3. At some point you find omega, very small written there, omega plus 1. So on the right, so the surreals contain the ordinals, but you have many more things. What is important is that you have a tree-like ordering, which you call simplicity ordering. And you say which X is simpler than Y if it is an ancestor of Y in the tree. So 0, the root, is the simplest element. And then you have 1, it's a bit more complicated, and we have 1/2 there. So 1 is simpler than 1/2, 0 is simpler than 1, and so on. You also have a total order which consists in reading the picture from left to right. You encounter some nodes going from left to right. So X, an arbitrary node X, is smaller than its right child, and also all the descendants of the right child. And it's bigger than its left child, and also all its descendants. So for instance, 1 is bigger than 1/2 and smaller than 2 in the picture, if you see these numbers, little numbers. 0 is bigger than -1 and smaller than 1. Okay, now you want to define, I have to introduce a small notation. X, if you have a node X, XL is a variable which ranges over all elements which are simpler than X and smaller than X. So simpler than X means that the elements simpler than X are those which are in the branch from X to the root. Some of them are bigger and some of them are smaller than X. XL denotes it's a variable ranging over the elements simpler than X and smaller, and XR simpler but bigger. Okay, let's define addition. X plus Y is defined inductively on simplicity. So you suppose that you have already defined some other sums involving simpler elements. And you define X plus Y as the simplest possible surreals, satisfying some inequalities which are necessary if you want an ordered field. So in particular, you would like the addition to be strictly increasing in each argument. And so you have to impose some inequalities, which are those that are written there. And you define X plus Y by induction as the simplest object satisfying those inequalities. Similarly, for multiplication, the inequalities become a bit more complicated because you would also like to have to impose some conditions which entail that multiplication is distributive over addition, because you would like to have an ordered field. Okay, it doesn't matter if you understand these definitions. The important thing is that very concretely, you can define ordered field operations on these surreal numbers. And these surreal numbers contain the real numbers. At level omega in the tree, you will find all the real numbers and also something else. You will see somewhere, if you look carefully, you will find square root of 2 somewhere, also Euler constant E, pi, and they are all at level omega. And but also you have at level omega, you also have omega itself, 1 over omega, and you have some infinitesimal, some infinite elements, and you have all the real numbers. This is the simplest definition of the real numbers as a subset of the surreals, much simpler than Dedekind cuts. So you can just say that the real numbers are those which are there in this tree, no? Can characterize them easily as a subfield of this object. Okay, now you can, now you want to represent the surreals as infinite, as a kind of generalized series fields. So you would like to define infinite sums. Infinite sums are also defined by induction on simplicity. In particular, they are defined as the simplest pseudo-limits of their partial sums. Pseudo-limit is a terminology coming from valuation theory. But let's make an example. Suppose you would like to define a summation of omega to the minus n. Okay, omega is an ordinal number in this case. It's not a variable, it's an ordinal number. But it's also a surreal number because the surreal numbers contain the ordinals. So you would like to define this infinite sum of omega to the minus n. You define it as the simplest possible surreals, such that for each partial sum truncated at k, if you take the difference, you would get something of the same order of magnitude than omega to the minus k, which is the first term that you have omitted, no? Comparable means, or the same order of magnitude means that each of them is bounded by an integer multiple of the other in absolute value. So that's it. This is a definition of infinite sum. Makes perfect sense in the surreals. Okay, now you would like also to define what is a monomial, a surreal monomial. Well, a positive surreal, it's called a monomial if it is the simplest element in its comparability class. And by some kind of miracle, you get a multiplicative subgroup of the surreals, the monomials. Also in the Laurent series, the monomials are representatives of their comparability class. Take any Laurent series is comparable with a power of an integer power of the variable. So the monomials always for people working in valuation theory, the monomials are a section of the valuation group with respect to the natural valuation. So you have defined infinite sums, you have defined monomials. You would also like to define an X. The definition of X is slightly more complicated, so I'm not giving the definition, but it's again by induction on simplicity. It's done by Gonchor, and I just give you some properties of the exponential function. Okay, how it is. First of all, you observe that some surreals are infinitesimals, namely they are smaller than any rational number and bigger than 0. Some other are reals, because the reals are contained there. The reals plus the infinitesimals form a subgroup, actually a sub-vector space of the surreals. The surreals form an R vector space. So you have a subspace which is given by the finite elements. Reals plus infinitesimals are the finite elements. You have a complement of this subspace, which I call which are the purely infinite terms, which I denoted with the arrow, and O with an arrow. Okay, then it turns out that you can define an exponential function which has this nice property, that the monomials are exactly the exponentials of the purely infinite elements. So the monomials, which have been previously defined, can be obtained as the exponentials of the purely infinite elements. Now you are in a position to define a normal form. Every surreal can be uniquely written as a formal series of the following form: a series of monomials times real numbers. The monomials can be represented in exponential notation. Each monomial is e to the gamma, where gamma is purely infinite. The monomials should decrease, so the gammas should form a decreasing sequence. And alpha should be an ordinal, the index set of the sum, and then you have real coefficients. So you start understanding that the trans series can be embedded in the surreal numbers, because you have omega is the formal variable of the trans-series, but it's also an ordinal. Omega, it's an ordinal it's a surreal. Omega, the surreal omega is a monomial. You can, and also log of omega is a monomial. So omega can be written as exp of log of omega. So you can start doing sums, and you have this normal form. Every surreal can be written in this unique way. Okay, what are the properties of this object? They are exactly the same properties, sorry. It's very similar to the properties of the real numbers. So the surreal exponentiation has the same first order property of the real exponentiation. First order, it's a technical term, refers to logic, but it's a class of properties. Very nice class, a big class of properties. Everything which can be said in a first order way about the reals with the plus times and exponentiation holds true also in the surreals. In particular, the exp must have an inverse. So you also have a surreal logarithm, because it's true in the reals, must be true in the surreals. It can be proved that omega, the ordinal omega, is a monomial, and also log of omega is a monomial, and so, and all the iterated logs. So it's a real closed field containing the reals, and also some strange numbers like the ordinal omega minus 1, or square root of omega, or log omega, exp omega. So it's you get a lot of new objects, which are kind of strange, but can be seen as, we will see that they make sense. Okay, then the surreals also contain a copy of the trans-series, because it suffices, as I said, to identify the formal variable of the trans-series with the ordinal omega, and you get an isomorphic copy of the trans-series inside the ordinals. Because you have infinite sums, you have exp, you have log, you have the same kind of ingredients that you have on the trans-series. But you have much more on the surreals. You have new objects which don't exist in the trans-series, and we will find examples in a moment. Okay, now the first difficult result is that you can define a derivation on surreal numbers, extending the derivation on the trans-series and respecting sums, exp, and log. So the derivation of the ordinal omega is 1, because omega resembles a variable tending to infinity. So for instance, if you want to the derivative of a normal form, it's easy to see what to do, no? The derivative of sum of r real times e to some power is just the sum of the real e to the same power times the derivative of gamma, because you want the chain rule to apply. So e to the gamma is a composition of exp and gamma. No, the idea is that these surreals should be thought as representing functions. So e to the gamma should be the composition of exp and gamma. But this identity itself doesn't define, it doesn't determine the derivative. For instance, just from this, you cannot see what is the derivative, for instance, of the ordinal omega 1. Omega 1 is the first uncountable ordinal. What is the derivative of it? You don't know, because, well, I know, you don't, in the sense that it doesn't follow from the fact, what I said before, because the omega 1 cannot be obtained starting from omega using sums, exp, and log. So it's just a completely new object, but nevertheless, it has its derivative. So how are we going to define, and I could give you explicit formulas. I could tell you what is the derivative. It's not, everything is very concrete and algorithmic. So how are we going to define it? The idea comes from Hardy fields. The heuristic considerations come from Hardy fields. What is an Hardy field? An Hardy field is a field of germs at infinity of smooth functions with the property that if the germ of a function belongs to the field, also the germ of its derivative belongs to the field. It's a very well-known object. You can find the definition in Bourbaki, and it captures the idea of non-oscillating behavior. For instance, you cannot have sine and cosine. You can have exp and log in a Hardy field, but you cannot have sine and cosine. Why? Sine has many cofinitely, unboundedly many zeros, so you cannot take the inverse 1 over sine, because it should be a field, remember. So the germ should form a field. So the zeros should be bounded, otherwise you cannot invert the germ, and should be closed under derivation. These are very much studied. And what we discovered is, first of all, that in any Hardy field containing the logarithm, there are some inequalities which are necessary in every Hardy field. Some inequalities involving derivatives and log, this one that I wrote. Log of the derivative minus log of another derivative should be much less than the two elements f and g in any Hardy field whatsoever. These are real functions. This simply must be true in every Hardy field. This is not the logarithmic derivative. It's the logarithm of the derivative, not the derivative of the logarithm. And so what we tried to do is we discovered that if we try to impose this inequality here together with the other conditions, you will find, we will discover a derivation on the surreals. So this is the heuristic which guided us in the discovering of this derivation. Aschenbrenner, Van den Dries, and Van der Hoeven gave a very strong, result, confirming a very strong confirmation of our heuristic, because they showed that every Hardy field whatsoever, field of actual real valued functions, embeds in the surreals with the derivation that we just defined. So we have a kind of universal domain for computing the germs at infinity of a lot of functions. So the idea is the surreals should be associated somehow to germs at infinity. This is the guiding idea. And then you also have integrals. We can prove that the derivation is surjective. So integrals exist up to a real constant. Well, to illustrate this, let me first introduce infinite products. Infinite products are very easy to introduce, because once you have infinite sums, exp and log, you can define infinite products in the obvious way. Well, now, the derivative of log n omega is a finite product of log 1 over omega, 1 over log omega, 1 over log of log. This is just a formula from calculus. You can, it's true, it's just a true formula for calculus. It's true also in the surreals. But now you may wonder, what happens if I take the infinite product of all these logs? Well, you can do it in the surreals. Not only you can do it, but you also can take the integrals, because I say the surreals are closed under integrals, not only in the derivatives. This is a completely new object, which in the trans-series doesn't exist, but in the surreals it does. And because the derivative of the n-fold logarithm is a finite product, this infinite product, once you integrate it, intuitively should represent a function growing slower than any iterated log. And all this can be made precise, but has been made precise by Van der Heuven and Bogoyoko in a recent paper. So you have all these new kind of objects. Now you can solve differential equations. Aschenbrenner, Van den Dries, and Van der Heuven proved that the surreals with this derivation behaves very much like the transeries, has all the good properties of the transeries with respect to all the first order properties as a differential field. In particular, it has a decidable complete theory, model complete. These are technical terms, but these are very important model theoretic results. In particular, as a consequence of these strong results, if P is a polynomial with coefficients over the surreals, you can solve the differential equations derivative of f equal P of f. So, of course, and the solution will be a surreal. Of course, you get this kind of differential equations are suitable for non-oscillating behavior. For instance, you cannot have sine and cosine because then sine and cosines involve second derivatives. This is only first derivative of f equal polynomial in f. But all the possible differential equations which make sense in a non-oscillating kind of environment, for instance, Hardy fields, they can also be solved formally inside the serial numbers once you have introduced the correct derivation. And I've almost finished my time, but I wanted to give some analytic application. Do I have time to do that or not, Giovanni?
Yes, please.
Okay, all this is very formal and algebraic, but we wanted to have some analytic applications. Of course, there are analytic applications of transeries by very important ones, by Dulac, by Ekal. I mean, a very modest analytic application. We wanted to give it also with the serials. So I want to present some partial results on a problem of Skolem, which is joint work with another ex-student of mine, Marcello Mamino, who is now in Pisa. Okay, this concern the study of the so-called Skolem functions. Skolem functions are defined in the following way. Essentially, they are the identity function x is a Skolem function. 1, the constant function 1 is a Skolem function. If you have two Skolem functions, f and g, you can take f plus g, f times g, f to the g. It's again a Skolem function. And these are inductively defined as follows. Okay, for instance, this example that I wrote here, x plus 2 to the x plus blah, this is a Skolem function. Some kind of iterated exponential polynomials, but without subtraction, without negative terms. You don't have subtraction. Okay, we can try to put them in normal form using the usual rules. F to the g plus h equal f to the g times f to the h. But it's very difficult to put them in normal form. Of course, they can be put in some kind of normal form, applying the rules, but we don't know the uniqueness of the normal form. This is a kind of open problem, I believe. Indeed, Wilkie found some strange equalities which are valid between Skolem functions, but which do not follow from the usual rules. This is an example. So the normal form, we don't know if we have a normal form. Nevertheless, I'm going a bit fast, I'm running a bit. One could, since you don't have a normal form, you may ask if, I mean, I'm a bit anxious because of the time, and give me an upper bound, really, Giovanni.
10 minutes.
Well, 10 minutes? Ah, okay, then I have plenty of time. Okay. if you have two scaling functions, you can prove that the difference has finitely many zeros. So that means that you can decide if two scaling functions are equal or not, because you just compute. If you have 10 zeros of the difference, you compute 11 values. If they are equal on those values, then they are equal. These values can be computed exactly without approximations, because a scaling function applies, if the input is a natural number, the output is also a natural number, can be computed exactly. So this theorem of Hardy also follows from a general result of Wilkie, which says that everything which can be defined, first order defined using plus times and exp, has finitely many connected components. So in particular, this difference has finitely many zeros. This is a very important result of Wilkie. But then you have finitely many zeros, but actually, you don't know how many, finitely many, but if you want an algorithm to test the equality of two scaling functions, you should give an upper bound. Not only, you know that there are finitely many, but you want an upper bound. This can be done. You can compute an upper bound on the number of zeros. It's kind of tricky. There is a more general result, actually, which is by myself and Servi, which says that everything that you can define using reals plus times and exp, not only has finitely many connected components, but you can give an upper bound on the number of components, computable upper bound. So you can define, you can prove, you can test the equality of scaling functions. Much more difficult is to define the order, asymptotic order. I mean, order for x tending to infinity. So f is less than g if f is less than g from some point onward. For instance, x plus 1 to the x is less than x to the x plus 1 for x going to infinity. Okay, given two scaling functions, you want to decide which one is bigger. You can prove that it's a total order, and each scaling function is bounded by some power of iterated power. It's actually a well order. So it's the order on the scaling function is isomorphic to some ordinal, because it's a well order. There are no infinite descending chains. For instance, if you start with x to the x plus 1 and you try to go down, you may try to go down finitely many times, but sooner or later you reach 1. You don't know how. So it's an intriguing order. There are incredibly two open questions, still open. Can we decide, is there an algorithm to decide, given two scaling functions, two expressions, which one is bigger? We don't know. What is the order type? We know it's an ordinal. Which ordinal? We don't know. It looks like a high school problem, at least the first one. Decide which function is bigger. We don't know. It's a particular case of the big open problem of the decidability of the reals with the exponential functions. The theory of the reals with the exponential function is not known to be decidable. There is a conjecture of, if one assumes Shanwell's conjecture in transcendental number theory, then everything is decidable. But without this conjecture, we don't know. Okay. What is our idea? To approach this kind of problems with very partial results using surreal numbers. You have a scaling function f of x. We may prove that this scaling function involves exp can be computed inside the surreal numbers. In particular, you can plug the omega for x. Omega is a surreal number. It's also an ordinal. And you obtain a serial number f of omega. F of omega now is a serial number which uniquely determines the function you started with. You get an isomorphic copy of the Skolem functions in the serial numbers in this way, preserving everything you want. Now you can expand f of omega in normal form, namely you can write it as an infinite sum. So as I said, we don't know if you have a finitary normal form. There is this problem of normal forms, which we don't know of Skolem functions, but you have an infinitary normal form going into the serials. Exploiting this infinitary normal form could be regarded as a kind of asymptotic expansion of f, in which no information is lost. If you try to expand with Laurent expansions or Puiseux expansions, you lose informations. But with serial expansions, you don't lose information. It's determined by expansions. So it's a super exact asymptotic, so to speak. Okay, and then I just, this last slide, with using this kind of expansions, we can prove actual analytic results. Despite the fact that everything seems formal, it has real analytic consequences. For instance, we can prove the following problem. Given a Skolem function G and a bound and a real bound M, if you want to consider all possible limits, real limits of f divided by g for x going to infinity below a given bound M, the given bound, then this set of limits is finite. So you get some finiteness result coming from these Skolem functions, which is not easy. And actually, there are this strengthens an old result of Van den Dries and Levitz, 1984, in which they proved exactly the same result, but limited to the fragment of the Skolem functions less than 2 to the 2 to the x. And the reason they could not go beyond 2 to the 2 to the x is that they were working with Laurent expansions rather than serial expansions. If you work with serial expansions, you have much more information and you can do the same kind of analysis, but for the whole class of Skolem functions. Okay, we can also compute the order type of some fragment. The first result below 2 to the 2 to the x was already known by Van den Dries and Levitz. We can go up slightly above, we can go below 2 to the x rather than 2 to the x to the x. We get an upper bound on the order type, which is the ordinal epsilon 0, which is an important ordinal in logic because it's the boundary between finitary mathematics and infinitary mathematics. It captures the strength of finite set theory with respect to infinite set theory. And Skolem conjectured that the whole class of Skolem functions should have order type epsilon 0. So the bound that we get is probably, actually, is far from optimal, very likely, but at least is a partial result towards. We didn't want to really, I mean, what I like about this is not the results itself, but the fact that they illustrate the fact that these algebraic abstract constructions can really have analytic applications because of various isomorphisms and embeddings that can be proved. So you have a universal setting for differential equations, x, log, derivative, integrals, everything formal, but also has potentially analytic applications. So I think I will stop here.
Many thanks for this very nice and interesting talk. Are there some questions, remarks? I have just a curiosity, if it's possible.
Yes.
In the real case, in the simple case, you can define the exponential map by using defining the log map by using integrals. For instance, you can define L of y as the integral between 1 and y of 1 over t dt, and you can recover the definition of the exponential function as the inverse of this function.
Yes.
If you have the notion of exponential, a global definition of exponential, by using a sort of integral, a new definition of integral that maybe you have, can you define this exponential as the inverse of
yes, I see. Yes, it's a very interesting question. It's not the way we did, certainly, because we did the other way around. You know? We defined integrals and derivatives, start having already the exponential and log function. No, because we first need to define an exponential function. Using the exponential function, we have some kind of exponential normal form. And then we know what the derivative does on this normal form, and then we try to prove that the derivative is surjective. So we never really define the integral. We simply prove that the derivative is surjective. Now, there is indeed the possibility of going the other way around. There is actually some recent work in progress with Mantova, Salma Kuhlman, and Matusinski, in which we are trying to do something of the kind you said. So we are starting actually with integrals, really. So there is a huge amount of work initiated by Rosenlicht in the 80s about something called asymptotic integration. So many fields and many fields of formal or fields of real functions admit asymptotic integration. That means that every element of the field has an approximate integral, maybe not an actual integral, but something which is asymptotic to the integral. There are many fields which are closed under asymptotic integration. And now there is the possibility of, in the surreals, there is the possibility of doing transfinitely many approximations using this asymptotic. So you have a function, you have an element, you compute the asymptotic integral, you take the difference, you try to integrate again. After transfinitely many approximate integrations, there is the hope of getting an actual integral. And actually, this kind of considerations are present also in our paper, now that I think of it. So actually, this is actually the way to prove that. It makes perfect sense what you say, and in some sense can be done. Starting with the work of Rosenlicht on asymptotic integration and iterating transfinitely many times. Thank you. It's a very interesting question. Yes.
Thank you very much. Thank you.
Okay.
More question? Maybe there is something in the chat.
I don't know if I see the chat. Let me see.
What happens if we move from the set of reals to the set of a complex number, a two-dimensional set? This is the question. What happens if we move from the set of reals to the set of complex numbers?
Another very good question. Unfortunately, here I am more pessimistic, and the reason is the following: that here we are. Everything that all the computations that we do are very concrete, algorithmic. There are no arbitrary choice. In particular, we don't use the axiom of choice. All the derivations, the integrals are defined explicitly, right? There are explicit formulas to compute everything. Now, if you want to define exp of omega, omega is a very large element. Exp of omega should be something which is, for instance, bigger than any polynomial in omega, right? But we have some kind of simplest canonical choice for exp of omega. So must be something very big, must satisfy some rules. For instance, exp of x plus y must be exp of x times exp of y. So, and these rules at the end determine a simplest solution that you call exp of omega. But if you try to do the same with the sine of omega, you cannot do it. What is sine of omega? Intuitively, it should be some completely random object between -1 and 1, no? Because sine keeps oscillating. At the end, when you arrive at omega, oscillates so many times that it's random. You cannot choose any reasonable value for sine of omega, right? Now, if you work in the complex version of the surreals, very reasonably from complex exponentiation, you also need to recover sine and cosine. But sine and cosine, there are no way to extend it to the infinite in a reasonable way without making arbitrary choices. So this is why we are limited to non-oscillating behaviors. So this is very much suited to analyze the asymptotic behavior of non-oscillating functions, like those living in a Hardy field, but not sine and cosine. So, and this is the reason, right? I don't know if this answers the question.
Okay. Thank you. Thank you, Mustafa, for your question. Some additional remarks? Patrizia?
They say goodbye.
Ah, okay, okay.
Okay, thank you.
Bene.
Thank you again. Thank you very much.
Non ci sono altre domande? Grazie mille.